Okay. Good evening, everyone. And we are discussing today uh, a very introductory session on reinforcement learning, and it is required in many aspects nowadays. A basic idea might help you. That was the motivation behind this session. So I won't be going into fancy mathematics, just how the engineering perception is required to get going. That's the main idea. I hope everyone can hear me. If there is any question or if there is any technical issue, if you are not able to hear me, just write something on the chat. I'm keeping my eyes on the chat, so I'll be able to respond if there is any need to interact. Okay, so let me start with the slide sharing. It is already shared. Okay, just a minute. So we are going to discuss reinforcement learning foundations, the very basic idea. And to start with, let me identify some of the recent developments in the area of reinforcement learning and why it is needed, why you are going to study it, and why we are discussing it. So the main motivation is some very recent breakthroughs in the areas of AI. For example, the reasoning revolution in generative AI 2024 to 2026 shift is actually based on something very interesting that came from the DeepSeek innovators, that is the GRPO. This is one of the reinforcement learning, I would say, engineering that worked really well. And you may be knowing that the RLHF, the reinforcement learning with human feedback, that thing was the cornerstone of the ChatGPT era. And so the reinforcement learning with feedback, the RLHF, that worked really well for the advancement of the the ChatGPT progress, the generative AI. And the next is, sorry, I was struggling with the AC. My room AC was not working. Anyway, now I have full attention to the slides. So the next thing is physical AI and the humanoid robots. The NVIDIA projects that, NVIDIA has a vast ecosystem. So there is one chat. Oh, my voice is low. Yeah, maybe the reason is my mouth was away from the speaker because of the AC that I was struggling with. It may be good now. Please let me know if you have any issues. So the physical AI and the humanoid robotics, that is another area, excellent innovations that are going on. I'm not sure how many of you know Isaac Sim. So this Isaac Sim is an environment where you can create robot models. I mean, you can import robot models and you can simulate its movement. And that way you can, in fact, I created one shop floor kind of environment. It's a virtual environment, right? So you can create a factory shop floor like environment where you can move robots. In fact, why not let us take a look? I mean, instead of me going, okay, I will come to this. Uh, Stop sharing PowerPoint and then maybe uh, for example, let me share. Yes. So the NV, NVIDIA Isaac same um, platform. If you go here, you'd see excellent innovations. This is the one, I mean, they don't have the use cases here. So use cases might be NVIDIA blog Isaac same. Yes, there may be the use cases. No, it's still not there. Yes. Yeah, robotics. So robotics in these cases, let me see the one recent example that somewhere I have seen. Mm, maybe it's not appearing. No, yeah, perhaps it's somewhere. I mean, in other areas. But what I want to say is that this kind of environment you can create, you can simulate. Yes, this is what I was talking about. This kind of environment you can you don't think that I mean it's very difficult to create all these things, a lot of software efforts would be needed. No, these models are already there. All you need is a very powerful machine, a very powerful GPU. And if you don't have powerful GPUs, no need to buy, you can rent it. So RunPod and Vast, there are other cloud computing GPUs where you don't need to pay upfront, but you can use their GPU services to run all these things. And so this kind of, okay, I don't make scratch marks on the screen. It's very distracting. If I don't know, I mean, let me remove this, try to remove the scratch marks. So the thing is, please don't make annotations on the screen. These assets. So what I was going to tell you is the assets. These assets are already there on Isaac same platform, and you can import them. You can create this kind of scene. And what is important is this. OpenUSD. OpenUSD is platform where this Isaac sim is based on, and you can simulate the robots in that virtual environment. You can create synthetic data set, and you can train your system. You can simulate your system. For example, if you are thinking of setting up a shop floor or warehouse, how things would go, where would be the aisle, how things would move. So all these things would, yes, there is a physics engine. So there is one question, how much accurate are those simulation with real world physics? So accuracy. So if you talk about accuracy, then I would tend to channel that beautiful quotation from George Box. All models are wrong, but some are useful. So it means, I mean, how much you need for your job. They are pretty accurate for the industrial needs at this point, but that depends on I mean, what you are going to do, right? But all I know is that for industrial automation, they are pretty good nowadays. In fact, there was one use case where, should I say, I don't know, maybe I would say in a different way. So some automobile part is takes long time to manufacture, and I mean, after quality checking, it reaches the production after a long time. But if you build a 3D model and virtually test it in this kind of simulated environment, then you can compress the lead time to a good extent. That was the idea. So that was what I meant when I shared this part of the slide. Slide. So, sim to real is a very hot topic in computer vision, robotics, reinforcement learning. The thing is, you train the robot or model, whatever it is, in the simulated environment, not necessarily robotics. I mean, for example, if you are, for example, what shall I say, the car, the automobile body, if you are interested in checking the drag, right? So you make it, you build it in as a 3D model, and you simulate it in a virtual wind tunnel and try to optimize your the car's body shape according to the simulated environment. And when you go to the real, as someone asked, how accurate it is, may not be exactly what you need, but it would be close to something that would require a lot of less iteration when you are building it physically. That is the thing. Sim to real. Sim to real means you are doing most of the things in simulation, and when you are going to the real part, it is taking a lot less time. So this NVIDIA project Groot, that's a recent outcome from India lab, and Isaac Sim I told you. But what array reinforcement learning really excels is at solving combinatorial optimization problem. For example, Atari, Go, this kind of games where you have really high number of state spaces. I would come to, I mean, the next slide has what I want to say about state spaces. So for this huge number of state spaces, it is very difficult to build a supervised learning algorithm, right? And that's why the reinforcement learning really helps in these areas. So with this, I mentioned one new term, that is state space. I should not uh, I should have not mentioned this, but I mentioned this new term, state space. So let me check what this state space really mean. State space is something that could be an alternative to reinforcement learning, but actually it is the limitation of supervised learning. Okay, let me simplify things. Let me not frame this way. I would say that supervised learning has a serious limitation, and that is the state space. And to describe you the state space, let us consider this drone. This drone is some UAV, right? And it is, when it is flying, it has got some orientation. It has got some, I would say, some orientation that I can use to describe its position in its, I mean, how oriented it is in the 3D space. So roughly, what are the measurements I would need? X, Y, Z, and then rotation around each of these axes. So not roughly, it is exactly the state space that I have described. So I mean X, Y, Z, and then maybe, no, not exactly, they are velocities. So linear velocities would be important. X dot, Y dot, Z dot, and then angular velocities around each axis. So omega X, omega Y, omega Z. So this constitute the state space. Why do I need all these measurements? I need all these measurements to describe its position in the air and its orientation, how it is oriented. Now the question is, if I want to move it in a reliable fashion, in a robust, stable fashion, then what kind of orientation would help me perhaps fly high, then land safely, then do all kinds of maneuvering? Is it doable with this state space? Yes. If I can make a correspondence X to Y, is X a stable configuration? If I describe Y as yes, or if X is not a stable configuration, then I can describe Y as 0. Stable configuration Y equal to 1, unstable configuration Y equal to 0. Exactly the way we train something in supervised learning, XY combination. But why it is difficult? It is difficult to get the paired data set of X and Y. So huge amount of possibilities exist in the state space. And if you, that's why I talked about this state space, and I'm talking about the continuous state space. So X, Y, Z, these are the continuous variables here. But think of this as chessboard. Chessboard is also an example of this kind of system. And what is the state at a particular time? At a particular time, state is defined by specific position of the chess pieces. How the black and white chess pieces are organized at a particular time. That is the particular state. Now, there are 64 the squares, 64 squares in a chessboard, and there are maybe around, I cannot tell exactly, I need to calculate, but maybe seven or eight pieces from black and the similar quantities of pieces from white. So you can imagine the explosive number of configurations that could be available at a certain point, right? It is not possible. It is not possible with supervised learning, because you need the paired data set. And since this kind of things do not work in supervised learning, we need reinforcement learning that teaches an AI to execute actions, evaluate consequences, and invent completely novel strategies. So this is something that I quoted from somewhere, but that is not the main point. You could have ignored this part. I got it from one of my past slides. So this is not very important. What is important is to for you to note that X and Y, this paired data set, is not always possible with supervised learning, and that's why we need something different. This is what reinforcement learning provides us. So let me tell you. So machine learning is broadly classified in three main categories: supervised learning, unsupervised learning, and reinforcement learning. What is supervised learning? Supervised learning means where I would say the X and Y, these peer data set are available, and unsupervised learning is where only X is available, Xi, and you try to see the structure in X. So if there are n data points, you try to find the clusters or the groups in this data set, and that is what is called unsupervised learning. Clustering can be an example of unsupervised learning. Topic modeling in text can be an example of unsupervised learning. Dimensionality reduction can be an example of unsupervised learning. And in all this unsupervised learning, you don't need Y. You need Y in this kind of setting where I would say the task is classification, regression, this kind of thing. You need supervised learning. But here the concept of Y is really vague. There is no way you can put Y. Maybe you can think of some way that supervision can be provided in some way, but not like this, not like this. So that's why this supervised learning, unsupervised learning are totally different from what we have here, that is the reinforcement learning. Okay, no question. Then we would leave slides, all this slide work, for the rest of this session. Perhaps we are not going to come back to the slide anymore. Yeah, let me see. Just a minute. I need to. Uh, okay, so I'm having some sharing issues. Just a moment, please. Resume recording. Okay. There was a slight technical glitch, but now we are back and we were discussing the reinforcement learning techniques, and we have discussed the motivation. And now we'll be moving to the fundamental ideas of reinforcement learning, and that need to go to the whiteboard. We need to go move on to the whiteboard. Okay, I can share the screen. That's lovely. And right now, let us think of this. Uh, yeah, we are doing good with time. So let me check if there is any question. No question. That's good. So, for example, I mean, when we talk about the fundamental idea, let us motivate our discussion with this nice example. This example, I would say that we got this example from the lovely work of Andrew Ng, Jagniti Agarwal, and Emma Brunskill. And I must give where the credit is due, and I must give credit where it is due. And definitely, I have not invented all of these beautiful theories. I have learned from somewhere, and my intention is to share all the beautiful resources that I myself used for learning. and so that you would be also excited to explore the beautiful world of machine learning, specifically reinforcement learning. So let us start this example that Andrew Ng frequently discusses in his lecture. That is the Mars rover example. The idea is this. If you have this kind of system, it's a I would say a grid, and we would actually eventually would move on to the two-dimensional grid. Now we are showing just one-dimensional grid. Suppose the idea is, suppose it's a Martian surface. I mean, I'm talking about the planet Mars. On the surface of the Mars, this is the Mars. On the surface of the Mars, perhaps one spacecraft is trying to land, and the ideal place would be point A. uh, there is another secondary site for inspection for scientific investigation, that is B. Site A is extremely important for scientific pursuit, but if for some reason, perhaps maybe there is a crater or something big that prohibits this spacecraft to move on to point A, then the second option would be point B. So this point A is, I would say, here, and point B is on the other side, right? And what we have, I mean, let me erase this. We have is, in order to move this spacecraft, when it lands on the Mars surface, it becomes a robotic exploration vehicle, right? We can call it the celebrated Mars rover, for example. And when we can take this robot vehicle to point A, we want to motivate it, right? We want to take it away. So when I'm talking about the motivation, I mean, we need to steer it. And to steer it, we need to speak the language of robotics. So suppose we get 100 points to get here and 40 points for the secondary inspection site. And these positions are called terminal state. These positions are called terminal state. Here, terminal state. Now, the thing is, when it starts from this different positions, for example, it has to land somewhere, and the best way to visualize this thing is to visualize in the form of a 2D grid. But since we do not have that much time, or it would be very complex to discuss 2D grid, eventually you would move on to the 2D grid, but now for the timing, let us stick to 1D for the appreciation of the basic ideas. Then we would move on to the 2D grid. We would do some Python coding too. But the thing is that when we, I mean, for example, this state is 1, this state is 2, these positions, I'm calling them state. These are our positions or state. Remember the state of the drone that I showed? The various configuration X, Y, Z. But now I have discretized this 2D space. I mean, this I would say the 1D space into 1, 2, 3, 4, 5, 6. So B is 6, A is 1. Okay, A is 1. Now, if the Mars rover lands here, then how can I take it to the terminal state, for example, A, or if A is not reachable, then B. Now, if the Mars rover in state 4, then how I can take it to the terminal state, that depends on various points. It would get some points. If it stays here, then the point is 0. There is no point for staying here. Again 0, again 0. But if it reaches state A, then the point is 100. Similarly, if it reaches this state, there is point 0. If it reaches B, then there is point 40. But in reinforcement learning, we don't say point. We say something that is known as reward, reward, reward. So the reward is for reaching this state 1. How we can compute this reward? Reward for staying in state 4 is 0. And if it moves, if it takes an action, if it takes an action to move left, if it takes an action to move left, then it reaches state 3, 0. Then it reaches state 2, 0. But if it reaches state 1, then it gets a reward of 100. Okay. And similarly, if it doesn't take this left moving action, if it takes the right moving action, then the next, it starts from state 4, then it reaches state 5, 0, and then it reaches state 6, that is 40. So you see that whenever it is reaching the terminal state, it is getting a reward 100 or 40, but the immediate movement is not rewardable. Immediate movement is not rewardable. So instead of, remember in supervised learning, we see X and Y. X is always paired with Y, but here the action, if you think of the action or state, whatever, if you think of it as X, then in the previous slide, I talked about state as X. So let us consider state X. If you think of this X coordinates as 4, 3, 2, 5, whatever, and then yeah, it's exactly like that. But what I'm trying to say is that this X is not paired with Y. Y is coming much later. That's why it is called, I would say the Y is delayed to some extent. So it is not immediate. And this is important in the reinforcement learning. So what the ideas we have explored here is reward. We are getting reward by taking action. So our action is encouraged when we are reaching the terminal state. And if we are not reaching the right terminal state, for example, we are not reaching A, instead we are reaching B, we are somewhat penalized in the form that our reward is minimized. So this way, our action is rewarded. So the concepts we have discussed here is reward, then is 2 is action, and number 3 is by taking action, we are moving on to the next state. So we have talked about state, and we have also talked about next state. Okay. So every time you take an action, every time you take an action, you move on to the next state. This is what happens basically every time you take an action. That is the core element of reinforcement learning algorithms, and will be deciding how to take action so that you get to see the right terminal state. That is the main objective, right? That is the whole purpose of reinforcement learning, is to learn how to take action. If we formalize this, then we have a fourth tuple, that is S. S is the state S. Is the state S. A is the action. A is the action. Here action is left movement and right movement. These are the action, left or right movement. And then there is something called reward. Reward. And then we have the next state. Reward is this reward. That is the 100 in reaching the left terminal state and 40 in reaching the right terminal state. This is the left terminal state reward. There is a right terminal state reward, and all the other rewards for for the remaining states are 0. So we have a four tuple. This is the next state. We denote next state by S prime. Okay, so there is one way of explaining this. I mean, you can write, for example, 4. If you take the left action, then you move on to the 3. And for this, you get 0 reward for moving on to the 3, the next state. And you get to see state 3. Okay. So this is how you move on by taking action at every state S in order to reach the subsequent state S prime. Now, this continuous sequence of states, actions, rewards, and next states form the essential data set. So we definitely have a data set. It's not that we don't have XY paired notion here, so we don't have data set. That's not the true case. State, action, rewards, and next state, they form the essential data set that reinforcement learning algorithms analyze. This is important. So where the data set comes from? The data set comes from this 4 tuple that I described. Now, by evaluating these 4 components at every step, the algorithm can learn from experience. So I'm mentioning this important word, experience. So we would see how it uses its experience to learn how it can move, right? So by evaluating this 4 components at every step, the algorithm can learn from experience and learn to do what? Learn to take the best action. Best in what sense? So these are the questions we are going to answer in the subsequent discussions. So the important thing is you'd asked me that I moved on quite arbitrarily from state 4 and how we can train the robot so that it can move with prior experience. So, for example, we won't be able to train the robot on the Martian surface. So that's why maybe, and it is done, we may train the robot in simulated environment on Earth, where it would gain experience to reach a terminal state like A. And if something goes wrong, then a plan B is also ready to move on to the plan B. So all these things require learning to take action. So state, action, rewards, next state, these are the data sets that would help the robot to learn how to take action while considering the state it is present at this moment, right? So we would train the robot to take the best action to take in the future, I mean, to maximize its objective. What objective would be coming to that part soon. Now, the thing is, when we are talking about this idea, I would introduce another idea that is, I mean, when we are talking about this reward, when we are moving in left or moving on right, we are getting some reward, but you can appreciate that reward is the ultimate reward that kind of guiding us is the terminal state reward, right? So we need to wait. we need to wait to reach the terminal state. And since the immediate reward is not helping us, we need to see and we need to gain from our experience. I told you experience. Experience is something that you gain by doing something for a reasonably long time, right? So there is something, a new notion I would introduce that is called return. Return. So return, what is return? Return is the sum of rewards. You can think of this I mean very simple form. It is the sum of rewards that you accrue, right? For example, in this case, what is the return that you get for moving from state 4 continuously left? So if you start moving for, I mean, let me stay here. If you start of moving left from state 4, then you get reward for being in state 0, and then you accrue reward for moving on to state 3, and then state 2, and then state 1, that is 100, right? This is how you get the return. But one important thing is that what happens if the battery of this robotic car, it is operated by a battery, right? Some power source, and it is energizing its battery from the solar rays, and for some time the sun won't be in the Martian sky, so it won't have this source of energy, so it is running on battery. And I cannot ask this robot to move indefinitely. So there has to be some penalty for moving around aimlessly, right? So we introduce something called a discount factor, a gamma. Gamma is a discount factor that actually minimizes the future rewards that you are going to get. It minimizes. So with the new theory, new concept, we have this gamma times 0 plus this gamma times 0 plus gamma, oh sorry, gamma plus I mean increasingly penalize. So it is definitely coming in the form of a GP series, not I mean gamma for all the states. It would be for first gamma, then gamma squared, then gamma cube, then 100, right? And this way, if I consider this gamma to be 0 plus 0 0.5 times 0 plus 0 0.5 square 0 plus 0 0.5 cube 100, then it is going to be 10. 10. For the ultimate return for moving from state 4 to the terminal state A is 10. That is the that is the return. That is the return we are getting. This discount factor is raised to a higher power. Remember, this discount factor is getting raised to a higher power with each passing time step. So the rewards is progressively downweighted. This mathematical adjustment effectively makes the reinforcement learning algorithm somewhat impatient. Right? Oh, sorry. I made a mistake. Yeah, right. It's somebody corrected me. Sorry. Yes, it's 12.5. It's 12.5. Yeah, please correct me. If I'm wrong, please correct me. Thank you. So Now the thing is, I mean, if you thank you. If you start from this fourth state, then three state, then second state, then one, 4, 3, 2, then 1, and then 5, and then 6. So if you move this way, so the reward would be, sorry, the return would be 12.5. This would be 25. This would be 50, and this would be 100. How? For state 2, if you consider for state 2, then 0 plus gamma times 100, which is 0 multiplied 0 plus 0.5 times 100. That is 50. That's why I've written 50 here. And similarly 25. 25, why 25? It's the same thing. 3, 0 plus 3, 0 for 3. That is the reward for starting from 3. Then gamma times 0 plus gamma square times 100. So it's 25. So this way, it's 25, it's 50. For what? For moving in this direction, in this direction. Now, remember, if you move from 5 in this direction, it becomes 6.25 if you move this direction. But what happens if you move on this direction? If you move rightward from 5, if you move rightward from 5, this is leftward, this is leftward, this is rightward from 5, u 0 plus 0.5 times 40. You get 20. You get 20 here. So the return, I told you the return is a new concept. That is the ultimate reward you get after reaching the terminal state. The return from state 5 is better when you move rightward than if you move leftward, because the secondary state, the secondary important state for scientific investigation is very close by. So instead of draining your battery and moving leftward and reaching the point A, it's much more efficient to move rightward and reach the state 6, because the return would be higher here. The return would be higher here, right? So that means again, if you compute here the return would be much lower here. So there is no point in moving from state 4 to I mean moving rightward from state 4. But there is a reason. It makes sense to move rightward from state 5. That is the idea. So how you move from different state depends on this discounted return, right? And this discounted return is also applicable in financial applications, because this discount factor represents the time value of money or interest rates, where perhaps the dollar value of Indian rupees X today, that is going to be Y tomorrow. So there is a time effect of money. Or when an environment includes negative rewards, the discounted mechanism encourages the system to postpone those negative outcomes. I mean, it discourages to take on those routes, and I mean, adjust the decision-making strategies accordingly. So ultimately, the total return depends entirely on the sequence of states visited and the actions chosen. By calculating and comparing the returns of different behavioral strategies, such as always moving left, always moving right, or choosing directions dynamically based on the current state, the system can identify the most efficient path. So here, what we are doing, in case you are wondering what we are doing, we are trying to identify how to take action while staying in a particular state. That is the idea, how to take action while staying in a particular state. Okay, that is the idea. Now, I told you how to take action. Now you can see now that we have something different. We have something different now, that we have this our Mars rover trajectory. This trajectory, 1, 2, 3, 4, 5, 6, and this trajectory, if you are here, the system is asking you to move left. If you are here, the system is asking you to move left. If you are here, the system is asking you to move left. If you are here, the system is asking you to move right. Remember, when you reach the terminal state, you don't need to take any action, because action is not defined when you reach terminal state. But here I am saying something, action. What is this action? We have seen states, we have seen for example, return, which is the sum of rewards. We have seen rewards. We have seen states. We know the next state, but how to take action? How to the red marks that I have signified here? Those are the actions. So how to take action that actually navigates my Mars rover, right? And that requires something that is known as policy. Policy. What is policy? Policy is a function. So I won't get into the mathematical stuff. I told you that otherwise I would be showing the mapping kind of stuff. So let us think of all these things in a very pretty non-mathematical way. So a policy is, this is policy. We would understand in a flowchart form. So policy is something that takes state as input, and action, it gives you back the action as output. So if you are in state 4, your policy at state 4 tells you move left. If you are in state 5, your policy tells you move right. So this is the policy. So I told you that I shouldn't give you the mathematical interpretation, but still, for those who are mathematically inclined, policy is something like, we denote it as a pi. This is the S to A. So pi S, sorry, is a function. Pi S is A. It's a mapping. It's a mapping from states to action that tells you what action A to take in a given state S. What action to take in a given state is. So pi 2, policy is guiding you to move left. pi 3. Policy is telling you move left. Pi 4. Policy is telling you move left. Pi 5. Policy is telling you move right. So it is policy that is dictating you. So policy, we have discovered something new today at this point. Policy. We have explored the state. We have explored the, what are the things? The four tuples: state, action, reward, return, discount factor gamma, next state S. But now we have hit on something new term, that is the policy. So policy is mapping that dictates or that guides us what action to take from a particular state. That is the idea. Uh, in reinforcement learning, our goal is to come up with a function. What is our goal in reinforcement learning? So definitely, I can hear your question. I can hear your question. How to get this red marks, red arrows that you have plotted here? I mean, definitely you have computed the return, that is the discounted rewards. You have computed the return, but what is the efficient way to compute this returns? Because these returns are guiding us. So you can sense that returns are the backbones of this policy. But how to compute them in an algorithmic way? So that is the crux. That is the crux of the matter. I mean, our goal is to come up with a function which is called the policy pi. This is the policy pi you can see in front of you, whose job is to take as input any state S and map it to some action A, and it wants us that the system wants us to take, right? So find a policy pi that tells you what action to take from state 2 or from state 5. That is the idea. Now, in summary, so let us do a summary of this. So I mean, this part so far. I mean, let me write it here. So what we have seen states, we have seen actions, we have seen rewards, we have seen discounted factor gamma, we have seen return, we have seen policy pi. Okay. So in case of this Mars rover, this Mars rover, my drawing is horrible, I know. This Mars rover, uh, this has got 6 states because these are the states, right? We have got 6 states. And what would be our actions? These are our actions. These are left, right, our actions. What are the rewards? 100, 0, 40, 40 our rewards. This is the 100, this is the 40. Our rewards, and discounted factor is 0.5, right? What is the return? Return is when you are in R1 state, you start from R1, your your reward is R1, and then gamma R2, gamma square R3, this way till you reach the terminal state. What is the policy? Policy pi. 1, 2, 3, 4, 5, 6, So your policy is this, this, this. Policy is not defined in terminal state. Right. So this is your policy. Now, what would be your something similar would be, for example, the drone that I showed you. The Oh, this is horrible. I mean, I cannot. Maybe a close something. This is my awful drone. I apologize for this horrible drawing. Now, this drone, what would be the states? It won't be like discrete. It would be something like X, Y, Z, X dot, Y dot, this way, right? So maybe a vector of 12 components. So it would be a vector of 12 components, right? Maybe I should write, otherwise you would think that it is infinite. It's not that. Omega X, uh, omega Y, and omega Z. And then action is, here action is the joystick movement. Joystick movement. And reward maybe for safe landing, this is +1, and otherwise there's a huge penalty, right? Discounted factor, maybe something 0.99. You cannot keep waiting, otherwise the battery would drain, it would crash. And similarly, R1 plus gamma, R2 plus gamma, R square, R3, this way, similar. Now, the real challenge is how to do this. How to do this. So what I showed you in a nutshell is a discrete, this is a discrete system, discrete state space, and there is a continuous state space. So this is discrete state space, 6 states, but this is continuous state space because it is varying over a continuum where the states in the Mars rover, it is taking discrete values here, discrete values. Okay. No question. Okay. The basic idea is done. Then I would move a little faster from this point. So at this point, we have come to the I mean real moment when we talk about the mathematical machineries that we would need for considering the reinforcement learning. The main idea is, for example, this Mars rover, it is positioned here, and it started moving. It started taking actions and moving towards the terminal states, right? So this Mars rover, we can call it as our agent. We can call the Mars rover as our agent. This is our agent. Okay. The agent is taking an action. This agent is taking an action. The action is A. This agent is taking an action. What kind of action? How it is taking an action? How it is taking an action? It is taking an action by following policy. Policy is guiding, right? Pi s of pi s equal to a. This is guiding us. This is guiding us. So agent is taking action by policy, pi s equal to a. And when it is taking action, it is actually interacting with environment, or world, or world, environment or world. It is interacting with environment because it is changing its position in the environment. And when it is changing its position in the environment, I made a discontinuity here because it's going in a loop. It's going in a loop. So actually, what is happening is just so there is a time sense. So it's better that I write everything. This AT is a time. Now AT is I mean in probabilistic way, you can think of this probability is maximum at 80. That's why I took this 80 for those who are mathematically inclined. Otherwise, you can forget it. You can forget it. You think of this one. So you can think of this pi st equal to 80. Okay. And then you actually move on to the next state, st plus 1, and you get a new reward. I mean, the reward for reaching st plus 1, that is the rt plus 1. And your journey ends here for tth moment. For tth moment, your journey ends here. The next moment journey starts. What is the t plus 1th? T plus 1th moment journey starts. But what happened before? What happened before the agent started taking action? Actually, the previous cycle gave us reward RT, and the previous cycle also gave us the ST. So this is how we read it. We read it that we were in ST, we got the return, sorry, the reward RT, and then we took action AT. We took action AT. Perhaps this is confusing you. Let me erase it. This is confusing you. Probabilistic stuff. So you are taking ST. You are staying in state ST. You got reward RT. Then staying in ST, you followed policy, and your policy directed you to take action AT. And when you took action AT, the agent, you means agent, the agent changes its position, and it went to state ST plus 1. It got reward RT plus 1 for that. This is in a nutshell what is called MDP. Sorry. This is called MDP, or Markov decision process. In Markov decision, why Markov? Because it based on this Markov chain assumption that your future state would be determined by your immediate present step. I mean, the previous step. It's so when you would move in t plus 1th, it is determined by st, not st minus 1, st minus 2, st minus 3. No, not that way. It is only dependent on st, and that's why it is the first order Markovian assumption, and that this is the reason that your future is dependent your present, or your present is dependent on your past. That's why this Markovian thing came into being, and we call it Markov decision process. If you find it difficult to, I mean, understand, it's okay, no problem. Just follow your intuition that agent follows the policy, and policy helps it to take the action. When it takes action, it moves on to the next state and reaps the next reward. It gets the next reward. That is the thing. You don't need to understand anything else. Not fancy mathematics is required, at least at this point. But the question is, okay, this policy, I understand this policy, what you are saying, that makes sense, but how I can learn this policy? That is the main objective, right? How I can learn this policy? For learning this policy, we need something that is called a new idea. Again, a new idea that is called state action value function. This state action value function. QSA. QSA. Why I'm saying this? Why I'm saying this QSA? Because I told you that pi st guides me to take action at, but actually pi st comes from a table. Pi st comes from a table, which is state, that is the table is pi. Oops. The state is 1, 2, 3, 4, 5. This is the state, and the action is this and this. This is Q S. This is the S in states. This is the S states, and this is the action. This is the action. So this table is named as QSA. QSA. And how it is guiding us? How it is saying that pi to move left? Because remember, I told you, because it is taking the maximum. It is taking the maximum. It is maximum here, minimum here, maximum here, minimum here. But it is different in no, in 4 or 5 or 5. Okay, maximum in the left movement, minimum in the right movement, but it got swapped. I mean, the reverse is true in state 4. The left movement is minimum, the right movement is maximum. 1 should not be there because it's undefined. Similarly, 6 is undefined, QSA. But that's it, right? So QSA, if I can learn this QSA table, then, which is called the state value function, then my purpose is served. Right? And then I can behave optimally. I mean, from state S onwards, I can behave optimally. That is the whole point. This is what I want to do. For example, if we go back to our where is that? If we go back to our grid, then 1, 2, 3, 4, 5, 6. Then I'm constructing QSA. I'm constructing this table. I'm constructing this table for your understanding. So for all the rewards are 0 here, and the terminal state 1 has 100, and the terminal state 6 has 40. Now let us compute the return. We are computing the return, and you know the return. Return is, what is the return? Return is R I plus RT plus gamma RT plus 1 plus gamma square RT plus 2, this way. this way, right? And if I compute this way, the left movement is 50, the right movement is 12.5. Sorry. Yes, no, I'm right. I'm right. Left movement is 50 because if you start from 2, 0 plus 0.5 into 100. It is 50. That's why it is 50. The left movement is 50. The right movement is 12.5. Left movement is 25. Right movement is 6.25. Left movement is 12.5. Right movement is 10. Left movement is 6.25. Right movement is 20. Left movement is, here it doesn't make sense. Just for the convention, I write this way. Now, if I compute this table QSA, can you now pick action? You can pick action now, right? You can pick action now. You can pick action this maximum. You are computing the maximum, choosing the maximums. So this, but here it is this. So this is the left movement. This is the left movement. Sorry. This is the left movement, this is the right movement. This is the left movement, this is the right. Left, right. This is the left movement, right movement. So if you have this table, you can select your action and you can move accordingly. You can move accordingly. So can I write this? Can I write maximum over A QS A? That is our objective. At every state S, I'm selecting my maximum over all A. Over all A. So at every state X, maybe state 5, I'm maximizing over left and right, and the maximum is right. So here for state 5, I would have 20. The value would be 20 because I would be maximizing over left and right, right? So I maximized over left and right and I got 20 because this is 20 for state 5. So if I have this the Q function, if I have this Q function, it is called Q function, then I would be able to take my decision. So now the ultimate value of the Q functions, you can understand it lies in helping you to make decision. So our objective is now we have come to the perhaps the last part of this session, that is uh, how to compute Q that I have been telling you for a long time. Sir, can you, so there is one question, sir, can you explain? Oh, there are a lot of questions. Let me see. 2 questions. So Shreyak Mitro is asking, sir, can you explain how the right returns are 12.5 and 6.25 and not for states 2 and 3? States 2 and 3. Did I make mistake? Two and 3. So let us compute 3. Let us compute 3. 0 plus gamma 0 for 4 plus gamma square for 5 gamma cube for 6, that is 40. So what is gamma cube? So gamma cube, just let me know, maybe. Yes, 12. Okay, it won't be 6.25. I guess it's be 12.5, right? What is that? Or maybe I'm making some mistake. 1, 2, 3, 4, 2, 3, 4, 5, or something. I mean, you need to compute. So state 3, 5. Okay, you are saying state 3 is 5, state 2 is 2 point, state 3 is 5. Okay, hang on. There is a confusion. So let me address the confusion. Um, okay, so you're saying is for state 3 it is 5. Okay, you're right. You are right. It would be 5. And then for 3 is 5, state 2 is 2.5. Okay, state 2 is 2.5. Okay. And then state 4. State 4 is zeros. So I suppose state 4, state 5 is okay. I know because we have done that. And state 4, just check if it is okay. Okay, thank you. Thank you for correcting this. State 4 is all right. Okay, thank you. Great, great progress. Yeah, I'm happy to see that you guys are computing with me. Being corrected is one of the happiest parts of this sharing this I would say the learning. Anyway, so since you got the main idea, where were we? Yeah, the point is that how we are going to take this task of computing Q. So computing Q actually rests on this idea. For example, I told you that this Q function is A is actually return RS. Now I mean, excuse me, I need to be a little bit mathematical at this stage because I need to uh, arrive at the algorithm. So we are plugging this in here. So maximum over A Q. This is the new state, and this is the new actions. So we are maximizing over all. For example, you can think of this as left movement and right movement. Okay, so whichever is maximum. So this is how we compute the QSA. So our what is our question? How to compute the policy? At this point, our question is how to compute policy, right? So our, I mean, search for an algorithm to compute policy leads us to this beautiful equation, I would say. And S is the current state, A is the current action, S prime is the future state, A prime is the future action that I would be taking after reaching S prime. And R is the reward of current state. And this equation is known as Bellman equation. This is the celebrated Bellman equation. And what I showed you here at the computations, uh, sorry, where did I leave my pen? Anyway, perhaps I don't need it at this point. The computation I showed you is the result of the Bellman equation, and the Bellman equation is the cornerstone of the entire this Q-based learning, I would say. And I need to move a little fast. Okay, I guess you have understood how the Bellman equation, works. Now, when we would be using this Bellman equation for learning, so in actual Q learning, so we need to, now you have got the main idea. Now we would be moving on to the algorithm part, Python code, and all those things. So I won't, since the foundation is already established, I won't spend much time on the basics thing. So now what I want to focus on is Q learning, how Q learning works. In actual Q learning, the agent doesn't know the true Q star, what I can say. I mean, true Q star is not, it's not a closed form solution that I can compute. No, it's not. I need to approach it in an iterative fashion. So the thing is like this. If I have, you have seen the 1D grid. I won't spend my time anymore on the 1D grid. Now let us compute the algorithm for a little advanced problem. So perhaps this is area, it's a grid world area, and we are looking at a 2D grid, and maybe a robot is actually waiting here, and it has to move on. This part. There is a flag. Then to move on this part, and this is death. Something like this. I'm so bad in drawing, or something like whatever. A death. I don't want to come want the robot to come here. So if it reaches this part, it wins. Now the thing is how Q learning can happen here. The idea is it would go explore this way, that way. It would continue doing stuff this way. Sorry, I got the, yeah, I found it back. So it would explore this way, and while doing that, it would iteratively, learn QSA. The Bellman equation would be iteratively applied RSA plus here, gamma max A Q S A minus Q S A. So when it is learning iteratively, the equation comes like this. Every time it takes a step, so this is what is called temporal difference. The way it works is TD, or temporal difference, temporal difference. It is actually simple. When I would show you the code, it is not that scary. It is simple. So our objective is to show you how it works for a grid world like this. This is a grid world. and it's a 3x4 grid world, and the robot starts from starting state is 2 0. What are the states? States are these coordinates are the states, xy coordinates are the states, and actions is up, left, right, down. These are the actions, and these are the prohibited state. You cannot enter this state. And this is the winning terminal state. There are two terminal state. This is the terminal state, and this is the terminal state. The first terminal state is the goal. The second terminal state is where you are dead. If you land on the second terminal state, the robot is dead. Perhaps there is a mine, and we are navigating a robot in a hostile enemy territory, right? So every time it takes a step, it uses the temporal difference error to update its old guess towards the Bellman equation target, right? We are learning a target Q. Alpha is the learning rate. So there is a combination between these two. Is the old value and this is the new value, and it is combined with this alpha. So this is how we are learning the Bellman equation in an iterative fashion. That is the idea. Now, if you learn this much of maths, it is enough. There is, I mean, for Q learning, it's nothing else is required at this point. How alpha controls what? Alpha controls how fast the agent overrides. How fast the agent overrides its old memory with new experience. So this is the new experience. So this is the old memory. This is the old memory, and this is the new experience. New experience. So over time, as the agent repeats this update, I mean, perhaps it's like playing a game, right? The agent is playing a game. Agent is the robot. Agent is the robot. It's playing a game, and it is learning over time. And every trial means starting from the starting state, initial state, and reaching either winning state or the what shall I say, the killer state. That, I mean, this one trial is called episode. Episode is one trial. One trial is episode. Now we learn QSA, this QSA iteratively over many episodes, over many episodes, many repeated trials. That way the robot knows how to move from initial state to the final state in this grid world environment, where there are some states you cannot step your toes on. For example, this particular state you cannot, and if you reach this state, you are dead, and that this state is your goal. You learn the Q function. For example, this Q function takes your movement. I told you, you learn the Q function by repeated computation of this over many trials, With this, I conclude the, this hand computation. Now I would move on to the code, the Python code. Okay, so let me give you maybe 2 minutes rest if there are any questions. Otherwise, we would move on to the coding part. Q learning. So what we did, we saw that what is return, that is the sum of reward, and policy dictates our action. Now, what is policy? QSA, the table is the policy. How we learn the table? If we learn the table, then we learn the this policy. And if we learn the policy, then we are able to navigate in an unknown territory. Our robot has learned to navigate in an unknown territory, but how it works? So this Q learning, I would be demonstrating with this grid world, that the grid world that I showed you. Remember that grid world. That grid world I showed you, we would be computing that grid world in this Python session. Any question? Let me check if there is any question. This approach of Q learning from the maths you showed. No, my friend, it's not. Let me show you why it's not. Okay, then I need to share my tab screen. Maybe it's coming out. And by that time, let me open the Google Colab. It appeared, yes. Okay. Okay, the Google Colab is on. Is it working? Okay, I guess so. Yeah, so coming back to the question, what was the question? This approach of Q learning from the maths you showed seems like exponential in complexity. So the thing is, if you look at, yes, the tab view is on. If you look at this equation, it is iterative in nature. That's one point. Another thing is that because of the Markovian, um, this Markovian assumption, computation of S is just dependent on the neighboring states. If you if you if you look at QSA, it just depends on the S prime, that is the neighboring state that where your action would take you, and the computation is restricted to this max, this particular max, this max. Now, if you are asking this, is the optimization maxing over a greedy search? Yes, it is greedy search. Now, if your question is, in that case, we may not reach the global optimum. If that is your question, the answer is yes, it is greedy search, but because of the mathematical properties of the Bellman equation, it is guaranteed to converge to the global optimum. It is guaranteed. I mean, so provided some crucial condition is made, but let us not go into that. I mean, if you are asking in from that perspective that some, I've seen some of the students are saying that it is a greedy search, so we are restricted to some local optimum, right? It's not. It's not. With this greedy search, the Bellman equation guarantees, this is the beauty of Bellman equation. And there are two things. One is learning the target policy, where you are actually this Q learning is called off policy. I mean, you are uh, playing it, I mean, trying the agent several different ways, many iterations, many episodes, it is learning. But the thing is, what happens if this particular grid world that I showed you, this particular grid world, it changes. Maybe the flag is not here in the next grid world, the flag is here, and the date is not here, the date is here. What would happen? What would happen? I mean, I won't answer this right now. I would come back to this answer, but I would let you think what would happen. I mean, is this a limitation of this approach, or can we do something else? I mean, perhaps I would consider it later, but it is not exponential in complexity because you are computing it from its immediate neighbors, and that is because of the Markovian assumption. And what remains to us is that the beautiful Python coding that we'll be seeing, that actually lets us compute this fairly fast. I mean, let me stop. Let me share here. Okay, you can see now. Yes, you can. Now, this is our action space because in the 2D grid world that I showed you. So our grid world is this. This is our grid world, and we would be controlling a robot. This is our robot. And this is restricted block. We cannot get there. And this is the goal, the destination. And this is the dead zone. Okay. So in this situation, what is our action space? So earlier in the 1D grid, our action space was left and right movement. But in this case, our action space is left, up, right, down. D is down, R is right. So these are the states. These are the states. 0, 0, 0, 1, 0, 2, 1, 0, 1, 2, 2, 0. These are our states. And this is our action space. 1, 1 is the wall. This 1, 1. This is the 1, 1. This is our wall. And 0, 3. Let me see. 0, 1, 2, 3. 0, 3 is our terminal. The terminal that gives me reward is 1. And the terminal that takes my life is -1, that is 1, 3. 0, 1, 1, and then 0, 1, 2, 3. So this is 1, 3. This is 1, 3, and this is 0, 3. Now, the thing is, the wall is 1, 1, and this is our rewards. I won't get into the other part. Let us remove this one right now. I don't need it. It would be, sorry. Okay. Okay, let me keep it here. I won't be referring to this right now. Depending on your understanding, I would show you the advanced part. So this is the environment. I told you about the environment. Environment is the what the agent interacts with, and these are the steps it takes at every step, right? The code actually starts from here. The execution. The execution starts from here. And this is the alpha. Remember, we combined the old experience with the the old memory with the new experience. Sir, could you please explain? So there is a question. Sir, could you please explain how the agent moves in the grid shown now? So here, this is the agent. Agent means our robot, right? And the robot moves in this grid. Now, this is zeros. So this is 0, 0. This is 0, 0, and this is 0, 1. This is, sorry, this is 0, 0. This is 1, 0. This is 1, 0, and this is 2, 0. Now, the agent can move, and this is 2, 1. The agent can move this way, or the agent can move this way. The agent, if it moves this way, it would be killed. It would go to the death zone. Now, the thing is, it cannot go this way because this part is forbidden part. I mean, this is a wall. The agent cannot cross this part. So this is forbidden part. Now, if it goes up, it can. If it goes right, it can. It can go down, and it can go left, right, both way. So the action space is, what is the action space? It's movement, right? It movement up, left, right, down. Up, left, right, down. It can go up. It can go up. It can move left. It can move right. It can move down. So the action space is up, left, right, down. Exactly that is what I've written here. The action space is up, down, right, left. And every state has the possible actions. These are the possible actions. I'm not telling which action is best, which action is not. We'll be discovering this. That is the goal of Q learning. But right now, this is the actions possible in these states. And the rewards. Rewards means what is the reward for reaching 0, 3, and what is the I mean the uh, penalty for reaching the dead zone, right? Now the execution starts here. When I call get grid, I get actions and rewards. Actions is this state to action, this dictionary, state to action, state to possible actions, not the state to optimal action. That is the objective of Q. And rewards is the 0, 3, the final rewards for reaching the terminal state. Now I create this Q table. This is the Q table. This is the goal for populating values. This is the Q table, right? QS. S is the state and A is the possible actions. For A in action space, I'm randomly populating it. Randomly populating for init. I'm initializing with random population, right? And then when I'm sorry, when I'm starting this, this is the episode, the repeated trial starts here. Repeated trials or episodes start here. This is the start state. 0 2 2 sorry 2 0 2 0 is our start state. This is 2 0 our start state. It is starting now. S is the starting state. While in S, I'm doing one thing. One is this one. I'm checking which action has the highest score in QSA table. For example, which action has the highest score? I'm taking this maximum. I'm picking the best action in terms of the highest score, QSA table. From QSA table, I'm choosing that A with the highest score. There is another trick. That trick is, this is not always I'm doing. I'm also making some random choice. And this is the classic exploration versus exploitation. This is the classic exploration versus exploitation. Why? This is the exploration part. Exploration part in reinforcement learning. Pretty famous. Exploration versus exploitation. So this is the exploration part. Let me, sorry. Oops, what I'm doing. Let me write it here. No, I don't like Google's this Google Colab's auto suggestion. Exploration part of reinforcement learning, and this is the exploitation part of reinforcement learning. Pick best action in current state, and exploration is, suppose somehow you got stuck at some point, so you are exploring newer areas for learning, right? Because this whole QSA, the idea is it would be average return at the end of the episode. You would be playing this episode multiple times, and that way you would be learning QSA. So what happens if you get stuck at some bottleneck, some loopy area? That's why the exploration part takes you out of that. So exploration is needed. Now, this is for choosing the action that would take you to the next state. This is the next state and the next reward. Next state and next reward. And when you reach the next state, this is where the maximization over all the actions, for example, left and right, remember? So this is the Bellman equation. So this is the Bellman equation. This is the Bellman equation that works. And you move on to the next state. That is the idea. Now, it would happen for 10,000 epochs. I would quickly show you. When I run this, I get this policy. This is the policy QSA. I'm actually, see QSA, this is actions allowed, and I'm actually plotting the after learning QSA, I'm plotting which state points me where. So see, I'm starting from here. It's up, up, right, done. So this way it's leading me to here. In fact, when I'm here, it is not saying R means right. If this state tells me to move right, I would be moving into the dead zone. It points me to up. So from here, I would be moving on to this state, and then I will be moving on to this state. That is the flag zone. I win the race. So that's it. This is the same thing, uh, copied twice. So that is the objective. If you play with this, you will be understanding the this how it works. You need to play with it. You need to do a little bit of uh, fine tweaking based on the theory that we covered. Any questions so far? I mean, if you compare it with the theory part that I covered, then you'd be able to understand how things relate to each other. Now, before concluding, let me tell you why it is necessary. So remember, we started with this application area, and this reinforcement learning is widely used in fine-tuning LLMs. And the reason is that if you fine-tune with regular supervised fine-tuning, SFT, then you need a lot of data. But with reinforcement learning, with human feedback, particularly DeepSeek, the GRPO algorithm, the data requirement is pretty small, and it works, I mean, converges pretty fast. This is the reason the GRPO algorithm is important for LLM fine tuning. So if you were wondering where you should go next, there are two possible ways you can go next. One is the GRPO, another is the supervised, no, not supervised. I mean, the question that I left you with, that what would happen if I change the grid world? What would happen if I change the grid world? I bring you a new grid world, or maybe instead of 4x3, it may be a different size. So this is the reason you need deep reinforcement learning, deep Q learning. This is not deep Q learning. This is plain straightforward Q learning. But if you want to generalize over a changing environment, you need to go to deep reinforcement learning. So you need to learn Q with the deep network. So a deep network would be predicting the QSA table. So state input, state should be vectorized. The action should be vectorized. And if you input them, the neural network would output the QSA scores. In this case, there would be four scores, because we have four action space. That's why the output would be four values, and over the four values we choose the maximum one, and we select our action. So that would be what is called deep Q learning or deep reinforcement learning. Okay, with this we come to the end of this session. Thank you for your interest. Thank you for your time. And there seems to be a question. How can we ensure explainability? How can we ensure explainability in those deep networks? That is the question of deep learning. Right now, in the reinforcement learning, we are not focusing on explainability, but definitely it's a question, and I would like to hear from you. What is your opinion on the explainability? How you want to approach this explainability question? I'm saying this because this question is open question. I'm glad that you asked this open question. So I would be curious to know what is your thought on this. And as I said, I have shared the Discord channel with you, because there are instances where interns want to get in touch personally. They want to have, they want to clear their own questions. They have some very interesting questions they want to discuss, or they want to explore new topics. You are welcome to get in touch with me on Discord. But again, Discord is not mandatory. It is totally optional one. It is born out of the need, a special need. It is not mandatory, irrespective of you join Discord or not. Your internship would go on as designed. Now you would get the next instruction from our TIH office. There was some unforeseen incidents, some reorganization is taking place, but I'm sure that your plan won't be disrupted. You would be knowing the next course of action pretty soon from the TIH office. If there is no other question, I see there is another question. How this is chosen, which path is best mathematically? It is maximization over QSA, maximization over action space. I mean, if you go through my theoretical notes, and if you go through the code, you would be able to understand. If you don't understand, you are welcome to contact me over Discord channel, or you can email me too. My email is shown, Sujoy at idstih.org. It is visible on the website. You can email me anytime. So, sir, can you please share the Discord link once again? Oh, yeah, I need to type on. Can anybody share, please? I'm seeking help. Let me see. For my friend, yes, I found it. HTTPS discord.gg 6A K capital WT, then T capital, then UR3H UR3H. Yes, you're right. Thank you, everyone. Good night then. Let me stop the recording. Stop recording.